minimize the loss function to do the.
But we'll talk about critical temperature for unsupervised deep learning autoencoders. Please. Thank you.
Okay. Thank you, Christopher. So I thank all of the in-person people as well as online people. It's the first conference I'm attending in person after the pandemic. Good morning to all of you. So the topic of my talk is going to be critical temperature from unsupervised deep learning autoencoders. It's based on this particular paper. Yeah. Finally, a clearer picture. So the topic that I'm talking about is the critical temperature from unsupervised deep learning autoencoders based on this particular publication up here. So let's go about mouse. Yes. Okay. Should I keep that lovely thing? Okay, so this is the outline of my talk where I first discuss the motivation that why in the first place should we try these things out, and then I'll briefly discuss the deep learning autoencoders which have been discussed yesterday by my peers here, and then I will just talk about how our model applies to the Ising model and the results, corresponding results, and then these are the further extensions that we have been drawing out, and finally the summary. Okay, so why do we need to study this in the first place? Being a physicist, the first thing that comes to our mind is what are the physics goals that we can accomplish. So the first thing that we can accomplish by doing this is we already know in Markov chain Monte Carlo algorithms that as we go towards the critical temperature or critical parameters, the MCMC simulations go through critical slowing down, and that basically enables us users to do any kind of simulation close to the critical temperature, and that's why we have come up with, I think for the past 30-40 years, we have come up with different algorithms. For instance, come up with the worm algorithm and these kind of algorithms to simulate close to the critical temperature. But then again, computing the observable is also a real pain, close to because of long range correlations existing in the system. So it becomes difficult to pinpoint the critical temperature. Exactly. So this is the first physics goal that we aim to achieve. And also, since we know that the observables that we compute through our simulations are suffering from finite volume effects, because we do on a finite volume the simulation. So as we increase the volume further and further, we see a dependence of the observables. And maybe we could get some observables, some information about the observables in the infinite volume if we have some machine learning inspired observable which has less finite volume effects. And apart from physics, the algorithmic goals that we need to understand is, first of all, we need to understand what's the domain of applicability of this particular autoencoders that we are talking about. And also we have to be very careful about the limitations involved in it. So going with this goals forward, so I'll just introduce, now this have been already there. I mean, you have been listening to this since yesterday. So it's just the objective of deep learning autoencoders are the learning features in a given data set hierarchically. And this is a typical structure of an autoencoder as we have inputs. And then slowly the information goes through the hidden layers, and finally it's synthesized into a latent variable, and then it's again decoded to get the final output. And at the end of the day, what we try to do is minimize this distance, basically take a difference between x and x tilde, and this whole operation should become identity. That's the aim that we try to achieve. So this is a typical autoencoder that you see here, and as you can see that we are slowly reducing the dimension of the information that we started with, and we're trying to compress the information as concise as possible. Okay, so yesterday by my fellow colleagues from Sebastian, you heard about variational autoencoders. How do we learn a distribution using autoencoders, and also from Cristoforetti, you learned about how to use convolutional layers in the version autoencoders. But today's talk is going to be just the autoencoders. It's not going to approximate a distribution, but rather the bare configuration that we start with. And I'll just discuss what are the challenges involved and what happens if we go about this particular idea. And so this is, I mean, you must have seen, this is a typical neural network, and this is, so what we start off is the input layer, it's the input data. For instance, I have 8 xi's here, and then, is it visible for you guys?
Yeah.
So what's happening here is, I mean, I guess, yeah. So the hidden layers is basically, you have a set of weight functions, which is wi's, which is basically connecting all the input layer points to each of the neurons here. And then we have a bias correction bj, and here we have this as input to the activation function, which is f, and f can be of different types here, as you can see, the sigmoid, tanh, and relu. So I will briefly also discuss the relevance. Why do we need such a structure to study physics through different models? Okay, so this is the typical structure here. Okay, now let's come back to the quintessential problem that we all have started our machine learning journeys mostly with, is the Ising model. So, I mean, I don't need to mention in details, we just know what's the Hamiltonian for this. And for our current setup, we are just dealing with the first term. This is set to 0. And then the transition observables that are involved in our calculation for Ising model. The first term is the magnetization, and then the susceptibility and the heat capacity. So these are different physical parameters that we extract through our Ising model simulation. And the 2D Ising model is basically more interesting because it has a phase transition. 1D is not that interesting. So, and other properties that we can compute are the observables. If we just study the scaling behavior, one can extract the B, which is a critical exponent, and gamma and alpha. So these are critical exponents for the observables. And the idea is very simple, as the Landau theory of phase transition says, that once we have the critical exponents, that defines the theory. So any physics is relevant to Ising model. If we have the same Ising and the critical exponents, we can say that we are studying the Ising model. Actually, it belongs to the same universality class of Ising model. Okay, so this is just simple starting point. So this, as I mentioned, that we try to, in autoencoders, we have an input configuration of size L cross L in 2 dimensions. We give it the input to the autoencoders, and here you again minimize. This is the mean square error that you'll have seen in earlier talks, which is basically trying to minimize the distance between x and x tilde here using this operator. So basically, we are trying to make this into an identity function so that x tilde is basically as close to x as possible. Anyway, so this is like, so what at the end of the day, what we want this whole operation to be an identity operation, right? And let's go back to this naive thing that we had in the beginning, what the neural network looks like. And the idea is like, why do we need such complex structures in the first place? I mean, we have Ising model, right? And we know that magnetization is just the sum of all the spins. You sum them up and you have a magnetization. And how can you achieve the same thing here? Suppose I just get rid of all the hidden layers, get rid of all of it. And what I have here is just one single output layer. And how will the machine learning optimize this thing? They will set all the biases to 0. If my wi's are all 1, which means that, and this function is just identity, because essentially we want identity. For instance, let's say for experimentation purpose, we just fix this f to be identity. Right? We don't use any of the activation functions. F is identity, these are zeros, wij's. If I look at low temperatures, where we have basically all 1s or all -1s, right? So this thing will just give me all summed up, which is the magnetization, right? this particular term, and we have what we want at temperature. We don't need all this complex structure if we just want to study equal to 1 or low temperature phases. But the complexity arises when we want to study a range of temperatures, right? Which has structure in it, which has, so if I, for instance, if I want to use the same model that we have all the input layers, no hidden layers, just one number. If I sum everything up, and with the same weight factors, what will I get at the end of the day here? So this will not suffice to be the magnetization, or it won't capture the quantity that we want to capture here, right? So that basically motivates. So since we have fixed the weights in the first setup with temperature equal to 1, we can't use the same weights again. So we need more complexity in this layers. We need more neurons which can capture features at low temperature, features at high temperature, and features close to the phase transition that we already know of. So that's the reason why we need so many layers. But then, since we are already working with, at the end of the day, we want to approximate an identity function. And what better if we just use the identity function itself as activation? But what will that happen if I just do the activation function as identity? Then it will activate all the neurons at once, right? If it activates all the neurons at once, what will happen is the features which are responsible to capture the spin, the latent variable at low temperatures will interfere with the features that you want to capture at high temperatures, because what this neurons are doing is basically activating certain regions for different parts of the temperature region. So if I am looking at low temperature, then a particular set of neurons are activated because of this activation functions, and what goes into the activation function, which are the weight factors, and we can extract that feature at low temperatures. And similarly, for different temperatures, we have different set of neurons which get activated. That's the reason we need a different activation function, because this basically is a continuous function which has compact support, right? So it tries to capture different features within this region. And for different temperatures, different neurons get activated because of this, because of different weight factors and X size. Okay. So, for instance, if I just train for, say, at one end, say I train for low temperatures, 1 equal to 1 to 2, what I see is just this. I mean, to get this, one doesn't need this big structure of neurons, right? One does not need so many layers. One can take 0 layers and just sum everything up with all the weight functions as 1, and then you can get what is shown here. But the complexity comes when you want to train for the whole range of temperature scales. So the same network, if I do not have activation layers, if I don't have layers or activation functions, then the same network can't be trained for over a range of temperatures. They are only valid at particular ranges. That's the reason why we need the structure of layers and activation functions in our setup. And then we have the activation is basically to switch off a particular neuron off and on, depending upon the temperature region where you are at. Okay. So this, moving on. So now that you heard about why do we need such a structure of neurons and activation functions to study phase transition. So in our setup, what we have here is basically 8 layers, and this has been found out through experimentation. To basically, you're trying out different ideas, like we're trying out different camera setups in the beginning. Similarly, in this case, we're trying out different types of different number of layers, and then different number of neurons in each layer. I don't know whether you can see this or not. So in the first layer, we have 625, then 256, and then 64, and then you have the latent variable with one neuron. And these are the two different types of activation functions they use. And you can see we are also introducing a dropout in between just to reduce the overfitting error or the bias that we have due to overfitting. So this is the structure that we have implemented for studying the Ising configurations. Okay, so yeah, so what we essentially do is we have the 2D lattice and we have basically L square set of numbers. We put in this trained network, and you just get the latent variable, which is just a number in this case, because we are doing just autoencoders and not variational autoencoders. So in this case, for each configuration, you just get a number, which is ZIConf. And this contains all the relevant information needed to study that particular configuration. So if I take this ZIConf and then so this is what the setup that we have is we have 40,000 configs in total over the temperature range of 1 to 4.5, and then we randomly choose 2/3 to train and 1/3 for the validation to test. So as you see here, we have 4 different volumes that we are performing this whole calculation for, which is 25 × 25, 35 × 35, 50 × 50, and 150 × 150. And as you see that all of them captures a certain feature as one approaches close to the actual critical temperature for the Ising. But this is still not a complete picture. So as you see that as we go from small volumes to bigger volumes, this gets steeper and steeper, right? And well, this is the idea that we are going to leverage, because we know in Ising, when we study different volumes, we have a second order phase transition. So we have a continuous change, which makes it difficult to pinpoint a particular temperature where the phase transition is happening. But given this particular setup, as you see that with volume increase, this is getting steeper and steeper, which is basically will enable us to pinpoint the particular temperature where this thing is happening. So this is what the main idea is behind to compute the critical temperature. This particular feature of this ZIConf getting steeper. So yeah, this is again what I spoke about, that if I have the magnetization, this is as you see, this is the second order phase transition. It smoothly comes down, and it becomes a difficulty exactly pinpointing where it is exactly transitioning into this ordered phase from ordered phase.
Can I ask something?
There's a question, I guess.
Yeah. Can I interrupt you for a second? Can I ask something?
Sure.
Okay. Can you say something about the train set? How did you choose the train set?
Yeah. So let me see. So you mean this particular slide?
No, I mean, how do you choose which temperatures to train, and so on? You made the point that you need the network to be able to train on a range of temperatures. So presumably you chose one temperature range. I mean, did you actually see that?
No, we actually tried different temperature ranges, like I showed here. For this, I trained for 1 to 2 temperature range, which does not have the phase transition structure in it. And you see just these two phase separated things. One and
so
one.
what's the axis here? What's the
this is again the ZIConf that you saw in the plot. I mean, this is the latent dimension basically. So if you train it for just the 1 to 2 temperature range where there is no phase transition, it's just two different possible phases, which is ordered phase 1 and -1. And basically this would mean that one actually do not need the whole structure of the neural network to study this particular temperature range, because everything is clearly either 1 or -1 is ordered phase, And as I said in the beginning, that one just needs no layers basically and just identity function, because you need to just add things up and you get latent variable and you're done with it. But the reason why we need such a complex, structure of neurons and activation functions is because we are not fixing a range of temperature 1 to 2. We are taking the whole range from 1 to 4.5 in our case, and it's arbitrary. You can choose any 1 to 6 wherever you think that there exists a phase transition point.
So to just recapping, you trained your model to have a phase, the ordered phase at t equals 1, and the unordered phase at t equals 2. Is that the train set?
No. And so the network does not know where the ordered phase and unordered phase are. It's independent, unsupervised. Right.
So sorry.
You are using
Yeah,
configuration of an extractor from all the possible temperature between 1 and
Yes,
2
yes.
in training, and the same in validation. Okay.
Yes. So yeah. So we are using, so as I said, I think 2/3 of the steps, the configurations in training, and 1/3 for the testing.
I see. Sorry. So you trained it throughout the entire temperature range.
Yes.
And did you see that the validation error changes in some non-trivial way throughout the temperature range? I mean, is it higher close to the transition or something like that? I mean, presumably you'd expect that close to the transition, more features will be relevant. So I don't know who's typing, it's not me.
Sorry, can you switch off your microphone?
So that's a good question. So what I want to emphasize is we are doing unsupervised training. So we actually don't know the configurations that go inside are is it low temperature or high temperature. It's basically a random to a uniform distribution. We choose configurations between 1 to 4.5. So the network itself, we don't initially know that what kind of configurations are going in it. It's training for all random configurations between 1 to 4.5. So it's a uniform distribution. Yeah.
May I say something with respect to the question?
Yeah.
So I need the mic, right? Hi. So Arnold, you were asking a question, right? So I remember there was a paper that showed that the loss looks like the entropy if you plot it with respect to the temperature. So I didn't write it, and I just vaguely remember it, but you're right, there is a certain structure to it.
And you can see the structure. I think if you train for higher and higher volumes, you will see that you can't get as much accurate as low in loss function as you can optimize for low volumes.
Oh, so at higher volumes you get it's harder to train. That's what you said?
Yes.
Why is that? Do you understand why is that?
Well, I can say, I mean, I won't say that I understand it completely. I can only say that given the complexity of the network in the beginning, that I mean, if you just look at this particular diagram, if there are more points in the input layer, one can safely assume that it will make it harder for fixing the weights, because it will take more time to reach a particular loss function value. Does that make any sense?
Yeah, I guess you have more weights. You're just saying the network is larger when the volume is larger.
Yeah.
There is also a question by Fen, if you in the chat.
Yeah. If the latent variable can only, so I'll just repeat Frank's question. If the latent variable can only take 1 or -1, how does the decode reconstruct the configuration for two values? The latent variable, well, since we are training for each configuration, so it's fixed, right? It's either 1 for that configuration. It's not a decision that the network has to make. It's 1 or -1. Given the configuration, it's 1 or -1 if it's a different configuration. So that's fixed. So there is no such issue of having multi-valued functions.
But the latent variable doesn't take just 1 or -1.
Yes, I mean, it depends on the volume, and also, I mean, it takes a range of values. It's not just, I mean, as I showed you, the latent variable, once you train for 1 to 4.5, this is a latent variable. So it's not just 1 or -1, it can take a range of values depending upon which temperature we're looking at.
Maybe it's the other plot where you are only looking.
Ah, I see here.
Yeah.
So here. So this is, if you train for 1 to 2 temperature range, then, I mean, given the configuration, it can take 1. And if because the network is same, right? The network is same for whether you are giving a configuration in +1 phase or giving a configuration in -1 phase. So depending upon the weight factors, it will give a different number. And so the Zs will assume a different value, right? No, sorry. Yeah. So here, as you see, if the weights are fixed once I train it, and then if this Xi's change, you know, sometimes I give a +1 ordered phase or -1 ordered phase, this will change this particular argument of the activation function. And depending upon that, if suppose I have a neuron which gets activated for say higher values, so it will capture the +1 Zi, and if it's a different argument for the disordered for the -1 phase, the other neuron will get activated and it will give you the other phase.
Maybe we can go ahead and then let the other questions for the.
Yeah, sure. How much time do I have?
Still 12 minutes.
Perfect. Okay, so it's a loss function translation invariant. Translation invariant. The loss function is the mean square error. So it is translation invariant. It doesn't matter where the points are. At the end of the day, you're just taking the difference between the points.
Sorry, can I elaborate, perhaps?
Yeah.
So imagine in the broken phase, like the top half of your lattice was spin up and the bottom half was spin down. And the network proposes a new configuration where the top half of the lattice is spin down and the bottom half is spin up. So it's kind of the opposite. You'd still say that those two configurations look very similar, even though every spin is opposite. So would the loss function give a high value in that situation, or would it be a low value?
So the particular setup that you're saying will basically be a maxima for the MSE, right?
Yeah, exactly. So, but this is a problem, right? Because you want the net, like we know that those two configurations actually are very similar. Or is that using too much of our own knowledge? No, but it's not, because it's like translationally. So what I'm saying is, if you imagine like every possible translation of the lattice, they'll all have a different MSE when you compare them. And I feel like you want to optimize for the lowest MSE.
Exactly. So the particular configuration that you're talking about won't appear here because that's a maxima. So the network will try to go as far as possible because that's the maxima. It will go as far as possible to that particular state as possible, as it can, to the optimizer, right?
Right, so it would favor states like that.
It won't favor, exactly, yeah.
No, but it should though, because that's a very similar state. It's just that it's
But this is the maxima for that state, right?
maybe we should talk about it after the rest of the lecture.
Sure, go ahead.
Okay, so just to comment to the question, so the states, so the autoencoder does not know, is not a physicist, so it does not know anything about this similarity stuff. So you're right in the sense that both belong to the same phase and both are low energy configurations, but for the autoencoder, these are the maximally different states.
Yeah, but I guess what I'm saying is, could we add the property of translation invariance, that piece of knowledge, to the neural network?
But what you're,
Yes,
so
I have.
this is not about translational invariance. This is about like the symmetry if you
Yes.
spins from up to down, right? That's what you mean.
So you will do a supervised.
Well, it could
No,
be
I think
translational invariance, because
Yeah.
if I just shifted the lattice by half a lattice size, I could make the two configurations line up.
Oh, wait. Are you okay? Are we talking about the antiferromagnetic or the ferromagnetic Ising model here?
This is ferromagnetic.
So
No,
you're
no,
talking about the antiferromagnetic, right?
Yeah, I think the general question is more whether we can design features that are inputted into the encoder decoder that have in them already certain type of symmetries that we think are important for the system, rather than the raw configurations of spins.
Yeah, exactly.
For example, suppose you have a gauge symmetry. Would it make more sense that the input fields are not the gauge fields, but rather some gauge invariant objects? I think it's a general question I was thinking of raising, but it's kind of slightly out of scope of this talk, I think.
Yeah, I think that we can discuss this later maybe when we go ahead now.
Yeah.
Thank you.
Yeah, thank you.
Go ahead. I guess the next slide. So after this, I was discussing this particular slide where we have the noisization and we have the. So this should go on sometimes automatically.
How to close it? Sorry. It was the hide. This one.
Hide floating meeting controls. Yeah, that should do it.
Okay. It was this one or
Yeah.
the first?
I'll just. Okay. So as you see that for the latent variable, this gets steeper and steeper, which is what my emphasis on. That this is second order, but this is displaying an order which we can't reliably say as second order. But the fact that it is getting steeper is just going to enable us to pinpoint the critical temperature. As you can see very clearly that if you do a second moment of the spins, as you can see here, this is the physical setup, and here you still have a wide enough peak, but here you have more pinpointed peak at a particular temperature, which is going to give you a more exact information of the critical temperature. Okay, so now the traditional technique that people in Lattice have been using is the Binder cumulants, which is basically trying to capture the non-Gaussian behavior of the Ising model. And since it doesn't scale in finite volumes, so you can see if you take the ratio for different volumes, it should exactly pass 1 at the critical temperature, which is infinite at infinite volume. So this is the physical, as you can see very clearly. All of this is the ratios for different volumes for 25, 35, 2500 and 3500, and they all cross this particular critical temperature, this particular line of 1 at Tc equal to the infinite volume critical temperature. But as you know that since we understand that since we do not have a second order phase transition and we do not know how it scales, finite size scaling, how it looks like, but this gives a slight idea that since it does not pass through 1 for this window cumulant ratios, it means that it might not scale as we expect for physical systems to scale. So, and this becomes more evident once you extract the TC through the peak of the susceptibility, which is chi z tilde, and you see that the scaling behavior looks very different from the physics scaling of the magnetic susceptibility and the critical temperature extracted through these two methods. And this is the theoretical value, which is we know from large unstaggered solution. And so this is the reason why we claim in the paper that this the model that the encoder is trying to approximate is not a model in the same class as Ising. The only thing that they share is basically a same critical temperature, but they do not belong to the same universality class. So we have to take what we get from machine learning with a pinch of salt all the time, and always make sure that we are studying the same physics. But anyway, so what we can extract the critical exponent through the scaling plots, and you can see there is a difference between the physics nu, which is 1 with uncertainty, and latent dimension is 1.6, which is quite far from the physical system nu of the Ising configuration. So the only thing that we can take back from this particular calculation is we can extract the critical temperature with an adequate accuracy because of the magnetization getting more steeper, or the susceptibility getting more steeper closer to the critical temperature. And as you can see that the scaling is more linear than what we have in physical setup, which means it suffers from less finite size effects compared to the physical system. And the things that we can conclude is it observes Z2 broken symmetry as we expected. And I think there's a typo here, should be universality. Anyways, so yeah, the thing that we can conclude is they share the same critical temperature at infinite volume, and it has small finite volume effects. And in principle, one can apply this model since it's unsupervised and it does not have any information what goes into it. You can literally feed in any model, which is 2-dimension or 3-dimension or 4-dimension, and you can see whether there is a phase separation and what you can get out of it. So this is a 3D Ising model, which has a second order phase transition again, and the critical temperature exists at 4.511. And I don't know if it's visible or not. This particular line is at 4.511, the red line. These are different volumes. And what we have tried to show here is if you use a different activation function, you get a different order for the phase transition, or a different steepness, basically. So if you use a tan H activation function, you get the steep behavior, which one desires to extract the critical temperature more accurately. But if one wants to get the order correct, then probably, as you can see, this stays almost a constant as it as the volume goes up to the linear activation function. So this, I mean, this is still a setup that we're investigating, but it might give us the order also correctly. But this is just a hunch. We have to compute it through critical exponents. And then you can apply the same for 4D Ising model, and one sees a similar thing as for different volumes. And the critical temperature is 6.65, and this is the red line here. As you can see, the same phase separation happens before 6.65. And the same continues for the Potts model. It's 3-stage Potts model and the 4-stage Potts model, and the critical temperature is 1.005, which is exactly where this particular symmetry gets broken here. And what's the reason behind we trying out different things? Because the idea of science in general is to be objective. So the network that we have, whether it can actually work for different universality classes. We know POTS model, 3D Ising, 4D Ising are different universality classes because they have different critical exponents. So if I can have the network which can actually capture this particular phase separation or this particular broken symmetry, we are in for something at least. We can. So this is the summary. So we know that the network that we have captures the broken symmetry for 2D Ising is Z2, for 2D POTS model Z3, Q equal to 4 POTS model Z4, and 2D Ising is continuous. So we know that the network that we have captures this particular broken symmetry quite well, which one can leverage to compute or pinpoint the critical temperature. And also we saw some significant effects of the choice of activation functions, which needs further investigation. So finally, I would conclude with an outlook that yes, this is just baby steps towards studying machine learning techniques on lattice models in rigorous ways as possible. And so now we have, since the models that I discussed, the order parameters are all some moments of the gauge variable or the field variable. So for Ising, it was like the first moment, and for other models, it's one of the moments. So it's a very simplistic setup. And obviously, it would be interesting to study where the order parameters are not moments of the field variable, but some more entities, as Sebastian has pointed out in one of his talks in U1, that the Polyakov loop was a non-trivial thing, which would be interesting. So that the next thing would be to look forward to gauge theories. And also, and pointed out as in one of the questions, that if we can somehow integrate in the loss function some other quantities to capture the symmetry of the system, it can be possible if you can include maybe energies, the Hamiltonian itself inside the loss function. Yeah, so these are the possible directions we hope to explore further. And finally, I'll thank my collaborators, Andreas, Dina, and Harris. And these are our new collaborators, Asperos, Avajia, Shiakas, and Vadachino. Thanks to all of them, and thanks to all of you for listening to me. Yeah. Thanks.
I think we have still time for a couple of questions.
Can I have a question?
Yes, please.
Yeah.
Could you clarify the TCs that you obtain? Is that for finite volume systems or infinite volume systems already?
TCs we are obtaining is for infinite volume systems, because we are, I think I showed you, let's show you.
Okay.
So this, sorry. Yeah, this particular formula, if you fit with two variables, which is TC at L equal to infinity and nu, one can extract the critical exponent nu as well as the TC.
Okay.
Exactly.
Thank you.
Hi, it's Biagio here from Trento. I want to thank you for the nice talk. I have two comments actually rather than questions. So the first comment is that even if you don't get the critical exponent, which obviously that will be part of my second comment, the fact that you get with such an precision the critical temperature with an unsupervised method, I think that is good. In the worst case scenario, I mean, since in a supervised method, you have the problem of choosing how, in an unbiased way, to start your supervision, you could use this as a guidance. So just to clarify, I mean, there are systems for which we don't know if there is a transition, if we don't know if there is an order parameter. Until we are playing with Ising model, everything is fine. But for those systems, I mean, understanding if there is space separation, this is already a good result. So this is the first comment. The second comment is actually a continuation of the other comment that was made before, and it's about symmetry. And I want essentially also to comment on Sebastian's comment that the autoencoder is not a physicist. So perhaps we could make the autoencoder or any other technique as much of a physicist as possible. I mean, teach symmetries, or better, embed symmetries in the loss functions if they are not there. Now, translational invariance is a difficult one with this method, but perhaps there is an easy fix with the Z2 symmetry, which is fundamental. So if you recognize two configurations as maximally distant, and they should be the same under Z2, so there is, I mean, it's not a big surprise that you get the wrong critical exponent. It's like if you are defining a symmetry breaking interaction in the Ising model. So an easy fix could be that you take the minimum of the distance between the configuration and the fixed configuration as the loss function. So this is not much extra work. And we implement the Z2 symmetry as an example.
Regarding translation symmetry, I have to comment there. So we know for antiferromagnetic. Oh, sorry. For antiferromagnetic model, we know there is a breaking of the translational symmetry at the critical point, and I don't know how much is that going to help if we already integrate translation if we were in the loss function, because it needs to be broken to see the broken phase, right?
You can, I mean, there is a mapping also there, because you can map an antiferromagnetic in a ferromagnetic.
Yes.
So,
Yes.
yeah, but I appreciate I appreciate what you are saying. I mean, the point is that if you know the symmetries, in a way, you will need to embed them in the loss function. Otherwise, we'll be defining another universality class.
Exactly.
So that was the essence of the comment.
Yeah.
So this is stage.
Yeah,
Oh,
Sorry. Okay. We can just ping pong between online and here. So Frank, do you have a question?
Yes. So it's a comment. So I've heard about this Ising model several times now. It was second day in the conference, right? And what I noticed is, well, we never talk about when we build these models, we never talk about if there's noise in the observation in the data, right? We always use perfect up and down configurations and all of these, or when we're dealing with this orbits, like everything is all good, right? But I wonder if there's any work where people are like saying, well, we have a noisy Ising model where we don't really know, like the data, the true data is up and down, but we add some broken bits to this configuration, and then just something like that, right? We don't really know what the configurations are, and then can you still do these like a phase finding this phase transition and all of these parameters? Can you still do that when there's noise? Well, yeah.
It's an interesting question, I must say, but I mean, it's something that we have to investigate, I guess. That's like Feynman said, shut up and calculate. We have to do that.
Okay. Just a question from here. Just 1 second. So we have another question here, and then you, Barak.
Yeah, if you don't mind, I'll just quickly ask mine and then pass it off to you, Barak. So it's a stage inventive. Nice talk to you. I just wanted to ask quickly in the spirit of the bottleneck talk from Sebastian yesterday. I mean, have you checked whether the Z that you're measuring is somehow related by some universal, say, nonlinear function to the magnetization? If you plot this in a correlation at various volumes, or does it change with respect to volume, or do you expect some sort of universal function?
I mean, we did do a correlation plot between the Z and the M's, and one could see that at low temperatures it's 1, as we expect, but as one goes to the broken phase, the correlation drops drastically, and the drop depends on the volume. The bigger the volume, the drop is more significant.
Okay, so it's not a universal correlation.
Yeah.
It's not well correlated at high temperatures.
Yes.
Can you also comment on that? Okay, so this is just a comment on the question. So I examined exactly what you were saying, and I noticed that when I go from an autoencoder to a variational autoencoder, I get a better correlation between the latent variable and the magnetization. And so I had in mind to basically define a machine learning model that reproduces the ability of physicists to find a phase transition. But what we've seen right now is even a lot better. So it's like in the autoencoder, I thought, okay, there is some deviation from the magnetization, so something must be wrong. But what you're showing is this deviation makes the autoencoder even better in discovering an accurate phase transition temperature.
Yes.
So yes, there is a difference. I also saw that, but you leverage this difference, which is quite cool. Thanks.
Please, go ahead.
Yeah, so I actually have, I think, a question and a follow-up comment to what Biagio was saying. So the question is whether the latent variable, I mean, is it true that unlike the magnetization, the latent variable does not transform under the Z2 by switching sign? Or it's some nonlinear transformation of the Isings. If I switch the sign of all the Isings in the input, will the latent variable also switch sign?
Okay. So
it depends on the activation function that you have. Whether
activation functions, yeah. And I think
So,
most of the activation functions that we have right now are all odd functions, right? Tan H is an odd function. So I would expect if you flip the signs in the input layer, the tan H will behave exactly the opposite how it behaved.
Okay. I thought, didn't you say you have a sigmoid somewhere?
Yeah. So sigmoid is, I think, is also
It's ReLU and tan H.
Sigmoid, I mean, the ReLU is, the tan H is, sigmoid is just some.
sigmoid is basically translated function, I guess. Right.
I don't think it's odd. In any case, my comment is that I'm not sure it's correct, but do we need to make sure that the latent variable has the symmetry we are, transforms under an irreducible representation of the symmetry group we are investigating? And in this case, should it transform, switch
So in
sign
this
or
case,
not?
we just showed that one does not need to worry about it actually. I mean, so right now the choice of our activation functions were just through experimentation will give the best loss minimization. It has nothing.
Oh
to
no,
do.
I see that, but then I'm wondering that the fact that you get the same TC but a different exponent is kind of intriguing, and I'm wondering whether it could be related to the way the order parameter is transforming under Z2 here. I don't know the answer. I'm just raising this. And the second comment I had is about how can we encode physical information into this construct. I think one way is with featureization. So make sure that think about how to use input features that have some physical attributes. I don't have an easy example with Ising, but I think that with certainly with gauge theories, it makes sense to use different type of Polyakov groups rather than plugging in the gauge fields themselves. I think it should allow us to use less data, possibly find a better order parameter.
Yeah, I think that is just a basis transformation, right, for gauge. One can use the infinite space of Polyakov groups instead as the basis.
Yeah.
Yeah.
Mm-hmm. Well, then one of the challenges will be to deal with the symmetry in that case, right? Because neither tan H or ReLU and all these things will not transform easily under ZN. but that should make it more interesting to develop new activation functions that have the right property.
Yeah, that's something we can investigate, I guess. Yeah, that's
On the subject of that comment, there's also been this interesting recent work, I think, by Andreas Ip and collaborators on convolutional neural nets that are gauge equivariant. And
Yes.
so I think they've worked out essentially this problem of what activation functions and what intermediate representations you should use for a gauge theory to get that right transformation property.
nice. That's interesting. Yeah. Thanks. Thanks, Paige.
So Parag, what you mentioned is basically have a kind of a reduction instead of having like a gauge theory with let's say 4-dimensional gauge theory with gauge fit, having like a 3-dimensional theory with where now the variables are the polynomials, right?
Yeah, in a sense, yes.
Okay.
And in fact, you can even enforce, because we know the phase transition in gauge theories does not have anything to do with translation invariance. We can actually reduce, put different averages on different type of Polyakov groups, and it will. I think once you use some physics insight, you will find that you need less data to train the model.
Yeah.
Even because you use some subject matter expertise and you don't need to teach the network to not break, for example, translation invariance. Or not, you don't need to teach the network to produce gauge symmetries, which is, by the way, amazing. I think that I don't remember who showed it yesterday. I think it's amazing, but I think you don't need to teach the network to do that. We know gauge cannot be broke. So that's I think the basic idea behind the featureization.
Okay, thanks, Barak. I think that we can thanks Paul again and close this session. Yeah. Thank you, Paul. Thank you, everybody. We now we come back here at 3 o'clock, I think.